Welcome, I'm Fredrik. I'm Norwegian. I work for Schibsted and I'm responsible for our blockchain efforts. So what I'm going to talk about today is, I'll give you a quick intro to the domain of blockchain and distributed ledgers. Talk about distributed consensus, what does that really mean? We'll talk about the Ethereum Virtual Machine and what you can do and build with the Ethereum Virtual Machine. So first, just to zoom out a bit, let's just think a moment about what is a bank. So a bank is essentially a ledger. It's a list of accounts and some values attached to them. So consumer, private, regular banking, that's what that is. And Bitcoin is essentially the same thing. It's a ledger. So a lot of people are confused about what is this something internet money. Well, it's actually just a ledger. It's a set of accounts and some values attached to those accounts. The difference is that the Bitcoin ledger is public. It's out in the open for anyone to copy, send around, and do whatever they want with. So the question then becomes, who decides? Who decides what goes in that ledger? So for the banking world, the traditional banking world, you ask the bank. You say, hey, what's the truth? What's in the ledger? And the bank will tell you, and you will have to trust that they, as the authority, will give you the truth. While in the Bitcoin ledger and the Ethereum, that's an open list of accounts and values attached to those, which anybody can access and monitor and verify. So, the big question then, how does distributed consensus work? How do you get to the truth of what is in this ledger? So, first let me say a few words about who participates, because this is really game theory, how these systems work together. So, you have the users, which control external accounts. And an account can store and send money, just like a regular bank account. And a user has a public key and a private key. And a public key is just your account number, essentially. Your private key is essentially your password. And what you can do with this is that you can sign transactions from your public key with your private key. And the whole network can verify that you are the owner of the public key without knowing your private key. And what you can also do is you can interact with contract accounts, which is different from external accounts. I'll come back to what this means. Then you have the miners. They have a few roles. They confirm transactions. That means they just update the bookkeeping in the ledger. They secure the network, meaning that they keep the history tamper-proof. So if I send you an Ether, the Ethereum currency today, you know that in 1 year it won't just bounce back to me. It's set in stone and it's irreversible unless you send the money back. And also the miners provide the money supply. And I'll get back to what this means, but this is the first time, blockchain technology, open blockchain technology, is the first time in history that we've ever been able to create a scarce asset without a central party controlling the supply of the asset. So this is a huge innovation. Also, miners run smart contracts. They run code, which is the Ethereum Virtual Machine. I'll get back to this as well. And then you have developers, which can write code and deploy it to the virtual machine. So you can create contract accounts, or what is called smart contracts, which is a piece of code that you can deploy to the Ethereum network. And it has its own account number, and it can do different stuff depending on the code you write. So Bitcoin is almost the same. So these things, the bottom bullet point for all these things, that's Ethereum stuff. But this thing and these things here is the same with Bitcoin. So essentially, the thing that Ethereum has is the ability to run code which anybody can deploy easily, where you have accounts which can be owned by code. I'll get back to that. So I want to walk you through a transaction. What actually happens? So say Bob want to move 1 Ether to her friend Alice. What he does, he takes Ether from his account and he broadcasts that a signed message to the network. So he declares that I'm the owner of this public key and I want to move 1 Ether to Alice's address. That piece of information, which anybody can see that must be valid even though they don't know his private key, is sent to the miners, and this is sent into a puzzle. And what actually happens here is that the miners, they take the previous block of transactions, the hash of that thing, they add transactions, which comes from Bob and a lot of other people, and they hash all that together. And together with that hash, they have to find a random number which matches some constraint. So you take transaction information, the history of the network, and you try to find a random number, which when you hash all these things together, you get a hash that has some properties. Typically, it has a certain amount of zeros in the beginning. And the more zeros you need to have, the harder it is to find that random number, which gives you that hash. So miners try to come up with this random number, which solves this problem. And when they have a solution, you will broadcast that to all the other nodes on the network. And they can very easily verify if that is correct. So even though it can be extremely computational heavy to find that correct number, to come up with a solution which matches the constraint, can be very easy to verify that this is the truth. And once someone has proposed a valid solution, effectively done a proof of work. So you've proven to the network that you have some hardware you're running, and you've spent some electricity on computing this random number to get to that solution. So anybody knows that you are invested in this network. And within that solution, there's money going in between different accounts, and there's also code running on the Ethereum Virtual Machine. And I'll get back to that. But baked into this thing, there's a bunch of transactions. And then this is added to the blockchain. So once every miner, every full node see that this is a valid solution, you will add that to the whole history of the network, going back to the first block, the start of the system. So that's how, and this process in Ethereum happens roughly every 15 seconds. And when a block is added to the transaction history, then Alice got her Bitcoin, her Ether. It's no longer at Bob's. And the miner which found the block is allowed to grant themselves new Ether. And that's where the money supply comes in. So there is no central bank, there's just computers competing in this game. And the winner, the first one to find a given block, will be rewarded with some new money out of thin air. So within a block, every transaction comes from the history of the network, except one, which comes out of thin air to the miner's address. And that's the money supply. And this is one of the main innovations in Bitcoin, is creating a scarce system without a central issuer. So we'll have a look at what's in a block. What actually is a block here? So this is the data structure. I'm not going to go through all of this. A lot of things are similar for Bitcoin. So what we have here is a data structure. In the header of the block, you have a parent hash. That is the hash of the previous block. So this piece of information for the last block, hashed. That goes into the next block, which means that you're connected to the history of the network. The nonce is it's a bit simplified, but it's the random number that you come up with to prove that you've done a piece of work. You have a timestamp. The difficulty, it's just a number, which when it goes up, it is harder. Meaning that you need more computing power to come up with the correct nouns to prove that you've done the work on the block. The beneficiary is just the miner's address, where the reward goes. And the number is the block number, so that just adds on, it's the last block number plus 1. And then you have some Merkle trees. I'm not going to go into the details here, but I'm just going to explain the concept. So you have the transaction root. So this thing is similar for Bitcoin. Ethereum has state root and receipts root as well. I'm not going to go into the details. But this is basically a fingerprint, a hash, which is a fingerprint of all the transactions that happened in this block within these last 15 seconds. So what that serves or looks like is this. So this thing goes into the block header. And then, so say there's 16 transactions. So each one of these bottom lines here, bottom boxes, represent transactions. So money going from A to B. And the thing here, the neat thing about this data structure is that you don't really need to have the information of all the transactions to verify if a transaction was included. So instead of every node downloading everything, every transaction that ever happened, you can have a light node which can store only the block header, which we looked at in the last slide, and there they have the root. So what's being done here is that you take two transactions, you hash them together, you add them and hash them, and you add them with another block and hash that, and so forth. And the thing here is that if I want to verify did transaction K go into the blockchain? Was it valid? The only thing I need is 4 hashes. So this is a tree with 16 transactions. And if I have 4 hashes, I can figure out if this thing was valid. So what I need is the L, so I can hash these two together and get this number. I need that one. Hash those together. I need that one, so I can hash and create that one. And I need that one. And then I can create the root hash. And I can see that that went into the blockchain, into the header. And then this thing must be valid. And the neat property here is that when the number of transactions increases, the bytes, the amount of data you need to verify every transaction or any one of the transactions increases much slower. So if we went from 16 to 65,000 transactions in the Merkle tree, you need 16 hashes to confirm that a transaction in the bottom section is included. And that is 512 bytes, which is not that much more than what we had for 16 transactions. So this gives you a very effective way of confirming whether a transaction was valid or not. Okay, so on to the Ethereum Virtual Machine. So what Ethereum lets you do is that you can create contract accounts, which essentially let you run code on the Ethereum Virtual Machine. So you can take a piece of code, deploy it to the Ethereum network, and it runs on all full nodes in parallel on the system. So everybody runs everything. You write in Solidity. It looks kind of like JavaScript. It's not the same thing, but it's pretty easy to to get started with. It's not that easy to really master, but it's pretty easy to we'll have a look at it. It's not that hard to understand initially. And these accounts, so you deploy an account, you deploy a piece of code, it gets an address on the network which can send and receive money, but it can't initiate transactions on its own. So someone needs to trigger it to do something. So you can send money to the account, and then you can say, okay, if I send this piece of data, then you should send the money to some other account. But the money there is only owned and governed by the piece of code that you have written. And the thing is that you take this code and you deploy it on all nodes. So then it's a question of who pays for that, because a lot of computers all over the world will run this code. So you have this concept of gas in Ethereum. So that is essentially something you have to pay to run code. So with these systems, there's economics built into everything you do. So basically, you can think of it as a market for running your code. So take an example. So different operations have different prices. And this is in gas, which is just a unit of account for the processing you want to have done. So if you want to add something, so then you pay 3 gas. If you want to multiply something, then you pay 5 gas. And if you want to, for instance, check the balance of an Ether account within your code, you want to check another account's balance, then it costs you 400 gas. And you bid on, you say how much you're willing to pay per gas. So this is a market mechanism. So there's a given amount of gas. So say one contract takes 10 gas to execute. Then you will have to bid on how much you're willing to pay per gas. And if that's enough for the miners to actually do the execution of that contract, they will do it, and they will get paid with the gas. So take a. Do
you prefer questions at the end?
What?
Us asking questions at the end. Otherwise, I have a quick one.
Yeah, do a quick one, but maybe we'll keep it to the end. Yeah.
Okay. Do the miners individually bid how much, what their lowest price is they're willing to accept?
Yeah.
Or is that they as the collective?
No, so it's up to every one of them. So they can pick up whatever things they want. So typically they'll choose to first process the ones where you have put in a high bid to get these things done. And then if someone wants to pick up your thing, then they can do it. So, but if there's a lot of people wanting to get code executed and you bid a low price, then you probably it won't be executed. So it's supply-demand thing. But any one of the nodes can decide to include it if they want to. So just one simple example here. If we want to double a number, if you do number plus number, then that's going to cost you 3 gas. If you multiply and do number times 2, then it's going to cost you 5 gas. So the whole mentality when you build these things is quite different from running regular code on a centralized computer or one server, because you have to think about all the time how you build it, how much it's going to cost you. Because this is going to run on thousands of computers forever. And it's going to cost someone to activate the piece of code. They're going to have to pay for that every time. So you really have to think long and hard about what you want to build and how you want to build it. Because computer resources is really a lot more expensive, and you have to pay for it when it's running decentralized. Okay, so what can you build with this thing? What does this enable? So if we look at tokens, so ERC20 tokens, that's Ethereum request for comment. These have totally blown up, and it's a standard for creating tokens. And what you do is you create some accounting on top of a smart contract or a contract account in Ethereum, and that is essentially a token. So what happens here, you map an address to just an integer, which is the token balance. And then you can, for instance, check the balance of any given address. And this function here will return the balance of that exact token that we're talking about in this contract. It's a constant, so it doesn't change the state of the Ethereum Virtual Machine. And then you can create a function where you let people transfer this token. So you can say that you want to send to some address and the amount of tokens, it's just an integer, and then you will have to require that the balance of the sender is bigger than the amount you want to send. And then the function will just subtract that amount of tokens from the sender, add it to the balance of the receiver, you'll trigger an event, and the money is sent. And this is essentially how you create and send a token. The thing here is that this is running on a decentralized, immutable system. So, if I create a supply, which is scarce, it is provably scarce, and you have effectively created a scarce digital resource on this system. And people can see that. So, while earlier you had to be probably a very old, very trusted institution to create a scarce asset of anything, I can essentially now prove to the world that I've created a scarce asset with some piece of code about something like this. And anybody can verify that this is actually the scarce asset. So this is a total game changer, because you can imagine this token being whatever. It could be stocks. I could say that my company, it's 100 stocks and I deployed it here, and anybody can see that I can't double the amount or stuff like that. And so this is the backbone for all, more or less, all the ICOs, initial coin offerings, done in Ethereum. And do you guys want to guess how much money was raised by doing stuff like this last year? $5.6 billion US last year. It's essentially this thing. That's it. It's of course a bit more complex, but this is the thing they're doing. They're creating just some accounting on top of Ethereum, which is then a token. And then you have some idea of how that's going to tie into something you want to build on top of Ethereum. But creating the token is this thing. Okay, but you have to be careful when you do these things, because this is an open system which anybody can access. So let's take an example. So you set a owner of a contract with tokens, and say that's the sender, so the account sending a message to this contract. And and if we have a function where you can change the owner, so you need to require that the person sending the message is the owner already, right? And then you can be allowed to set owner. So one project, it's a bit simplified, but they sort of forgot to put in this line. And they had a multi-signature wallet controlled by their account. So there was a bunch of accounts which relied on a signature from that exact wallet in order to move funds. And then they forgot to do something like this. And so some random guy came in and managed to set himself as owner of that account, which was controlling a lot of funds. And what he did was that he killed the contract. Random guy goes in, makes himself the owner of the contract, and he killed the contract. That contract controlled $450 million.
Was it easy?
And yeah, so this is was a on-chain wallet called Parity. And this money is basically lost forever. Since that contract was basically the admin of those money, and that contract doesn't exist because he killed it, it's basically frozen up forever. It's about 500,000 Ether, which is currently 450 million Ether, might be much more in the future. So these are the type of things that you can encounter if you don't do this right. Or if you just put that line under there, then you have the same problem. So you really have to think long and hard about these things and test it. And so very important to have security in mind all the way. Another example, so this is something called Etherisc. It's a project that's live and working. They have a bunch of stuff on GitHub if you want to check it out. But it's basically a flight insurance. So we have a smart contract running on Ethereum. And if you're a passenger, you can say, hey, I want flight insurance. I'll pay the insurance premium to the contract. The contract, running decentralized autonomously, will fetch some flight delay info for my flight from an oracle. And if my flight is not delayed, then it will just take my money. And it will be stored there in the contract at the contract address. If it's a delay, then I'll get the predefined amount that I'm to be paid, so say the double amount, for instance, I'll get it back. And this thing is essentially an insurance company. It's running on its own all over the world, and the only fee you pay is essentially to keep it running. And it's an insurance company where I can see how much money is in the insurance company. Everything is transparent, everything is open source. I can see what kind of exposures it has. I can check which flight it covers, which open policies it has. So this is a pretty big deal. And it runs, like when insurance companies say like they look into blockchain and stuff, and maybe they try to like cut costs by 20%. Like this thing runs at like 1,000th of the cost, or even less, of an insurance operation. So this is a total game changer. And it's actually pretty easy to get started with this. So you have the programming language, which is Solidity. There's an IDE called the Ethereum Remix. It's very easy to play around with it and see what happens. You have the SDK Truffle, and I don't know how to pronounce that. Ganache, something. Ganache, which is basically running a local blockchain on your computer, and it's pretty easy to set up with these things. So it sort of looks like JavaScript. It's a lot of good tools or tutorials out there. And then it's really easy to get going with these environments, and you can actually build smart contracts which do whatever you want, which is essentially programmable money. So to round off, yeah, you can take a picture of this. What is this? What is this whole thing? So essentially, it's an open and secure global peer-to-peer payment system. And that's cool. I think a lot of people underestimate what open really means here. So no one really gets to touch the core infrastructure of a bank. Like, it's like locked away. That's the whole security model. In this world, it's like bent inside out. Everybody can access. Anybody can try to attack this thing. Everybody can access it and copy it and do whatever they want with it. And when I like to use this analogy for what I'm thinking open means here. So Microsoft Encarta, that was a encyclopedia done by Microsoft It cost about $400 a year, and it had 62,000 articles. So that's great. Guess where I learned about Microsoft Encarta? Yep. Wikipedia has 40 million articles, and it's free. And today's banking system and services is this. It's something that's pretty limited and quite expensive. But now, with this new world, we're going to move on to the Wikipedia for finance. Anybody, any of you can go home, download Truffle, play around, and create a financial instrument, product, even an organization, and deploy it as you wish, play around. It's insane amounts of innovation possible here, and it's a whole different world from what we know. And some people go, oh, well, but maybe the banks will do this. Well, Truffle is downloaded almost 300,000 times. That means that, and it's going through the roof. That means that it's almost probably up to 300,000 developers looking at Ethereum right now. Google has, as far as I know, around 35,000 engineers. So you have almost 10x the amount of engineers at Google already building stuff in this world. So the banks can shout innovation and whatever they want, but it's on a whole different scale. So I really encourage you to go out, download these tools, and play around with these things, because it's extremely powerful, and it's not that hard to get started, and you can really do mind-blowing stuff. So thanks.